Welcome back. In the last class, we figured out that Gina, who will ride for the apples next summer, has a 9.1% chance of riding more than 35 miles. In this class, we'll predict probabilities for other outcomes in next summer's rally. Let's start with this one. What are Gina's chances of beating her older brother, Joey? To answer this, we define a new random variable equal to the difference between Gina's m and Joey's m. Let's call this variable Gj. When Gj is a positive number, Gina beats Joey. If it's negative, Joey wins. We start by building the probability distribution for Gj. To do this, we need to know the mean value of Gj, or Gj hat, and we need to know SE for Gj. Gj hat is equal to m hat for Gina minus m hat for Joey. We know that Gina's m hat is 30.2. Using his GR, GE, and IN scores, the regression equation tells us that Joey's m hat is 34.0. We subtract 34 from 30.2, and the result is minus 3.8. So that's Gj hat. So what is SE for the distribution of Gj? Mathematically, SE for a variable that is itself the sum or difference between two other variables is equal to the square root of the sum of the squares of the SEs of those two variables. We know that Gina's SE is 3.8. Joey's m hat is 34, so the 12% rule tells us that his SE is 4.1. So we can rewrite the equation for the SE of Gj this way. When we do the math, we find that the SE of Gj is 5.6. We now have the probability distribution of Gj with a mean of 3.8 and an SE of 5.6. And we want to find the probability that Gj will be greater than 0, in which case Gina beats Joey. Opening up the HackMath probability distribution calculator, we enter the mean of minus 3.8 and an SE of 5.6 and specify 0 as the target on the x-axis. The calculator tells us that the area to the right of 0 under the curve is equal to 31%. So Gina has a 31% chance of beating Joey. Here's another problem. Remember that next summer's riders will be members of riding clubs similar either to the apples or the oranges or the grapes. What's the probability that the average apple rider will beat the average orange rider? To solve this one, we define a variable that is equal to the average apple's m minus the average orange's m. We call this variable AO. When AO is greater than 0, the apple wins, and vice versa. AO hat equals m hat for the apple minus m hat for the orange. A regression equation tells us what the m hats are for the average apple and the average orange. And when we subtract the apple from the orange, the answer is minus 4.3. So that's AO hat. Now what's SE for AO? As we saw a minute ago, the SE for the difference between two random variables is the square root of the sum of the squared SEs of each variable. We know the m hats for the average apple and the average orange, and we can use the 12% rule to calculate their SEs. Plugging these SEs into the equation, we find that the SE of AO is 5.1. Finally, we ask, what percentage of the area under the curve lies to the right of 0? That's the probability that the average apple will beat the average orange. When we plug the mean and SE of AO into the HackMath calculator, it gives the answer 20%. We can do the same exercise to calculate the chance that the average orange will beat the average grape, and HackMath tells us the answer is 16%. And the chance that the average apple will beat the average grape turns out to be 4%. In the next class, we'll look at how a rider's odds of finishing the top 20% vary depending on his GR score. To get ready for that, I want to end the class by talking about percentiles and how we mark them. We refer to the M score that separates the top 20% of all riders from the bottom 80% as the value of M at the 80th percentile of the distribution. Using the HackMath calculator, we solve for the value of M at which 20% of the area under the curve lies to the right. This turns out to be 35.3. So that's the score at the 80th percentile of the M distribution. 80% of the scores are at or below 35.3, and 20% are at or above 35.3. M hat is the score that separates the top 50% of the distribution from the bottom 50%. So M hat is at the 50th percentile. And the value of M at the 20th percentile of the distribution turns out to be 28.9. Now, we don't have a probability distribution for GR scores, but we do have the scores for last summer's riders. Here they are, ranked from lowest to highest. What score is at the 10th percentile of this distribution? Since there are 30 scores in all, it's the one that divides the bottom 3 scores from the top 27 scores, and that score is 1. The score at the 25th percentile is the one that divides the bottom 7 scores from the top 23, and that score is 3. The score at the 50th percentile divides the top 15 from the bottom 15, and that score is 6. The score at the 75th percentile is 8, and the score at the 90th percentile is 9. In the next class, we'll ask, what are the odds that a rider with a GR score at each of these percentiles will have an M score at or above the 80th percentile for M? I'll see you next week.